Okay, graphing trig functions. Some of you are very artistic and will do a nice job drawing your own. I also have some special graph paper for you if you would like to use this to graph your trig functions.
Yes, please.
Okay? So if you don't mind, take some and kind of pass them around. You might want probably a couple sheets each.
I need to teach myself how to
It's a
write.
good name cards.
What is that called? What? But then you guess.
What's narcoleptic?
Alright.
Narcolepsy? Can I have another one?
We're going to graph the sine function. We're going to graph y equals sine x. Okay? One thing when we graph these, we'll always be in radians. Okay? We're always going to be in radians when we work on these graphs. The book may do some in degrees. Okay, so I can show you how to very easily change it to degrees, but we're going to be working mostly in radians. Okay? Way back when you first started graphing anything, do you remember making a table of values?
Yes.
Okay? Miss Carey said, put -2, -1, 0, 1, and 2 into your table of values, and then you plug those in and see what you get for y, right?
Yeah.
Okay, awesome. We're kind of going to start with that idea, with trig functions. Okay? So what I'm going to do is, let's just start with 0. You should know this. If I plug in 0 for x, what do you get for y?
0.
0. You guys know that from your time test, right? The sine of 0 degrees is 0. Right? So there's our first coordinate. 0, 0. Okay? Now, I'm not going to write in some of these next ones here, but I'm going to go up by degrees because we haven't practiced radians too much yet. What's the sine of 30 degrees? 1/2. 0.5, right?
Yep.
What's the sine of 45 degrees? Square root of 2 over 2. Somebody with their calculator, tell me what that is as a decimal, please. Square root of 2 over 2. 0.7. So it got a little bigger, right? Okay. How about sine of 60?
That one's
Square root of 3 over 2. See what that is as a decimal. 0.86, right? So it got even bigger yet. Okay? Let's go to the sine of 90. 1. Okay? 90 degrees is also pi over 2, correct?
Yeah.
Okay?
I really didn't realize that.
Pi over 2 is like 90 degrees. So at pi over 2, I'd be up at 1. But as I went from 0 degrees to 90 degrees, my y values kept increasing and got all the way up to 1 now, right?
Yes.
Because sine of 30 was 1/2, sine of 45 was 0.7, sine of 60 was 0.86. It was slowly getting bigger and bigger, and now it got to a value of 1, right? Okay, so let's go past 90. Let's go to 120. What's the sine of 120? Root 3 over 2, so it's back to 0.86. So it's headed back down now, right? Okay? Think about your unit circle. Sine is your y value, correct? Does your y value ever get bigger than 1? No. So at pi over 2, which I'll just kind of make my first mark, I'll say that is pi over 2. Okay? So my first tick mark over, let's label it pi over 2. It gets up to a y value of 1.
Why is it?
90 degrees.
Yeah. So okay.
But when we're not graphing this, we're not labeling these in degrees, we're labeling them in radians. Okay? So each tick mark is going to represent pi over 2, which is what, about 1.57 units? This pi is 3.14 units, and 3.14 divided by 2 is about 1.57.
so it's
I
not
was confused.
exactly-
We're not counting by ones, is what I'm saying. Each check mark is not going to be 1 unit. Okay? We're going to make this easy on us.
Wait,
Yes. So
that one up there, that's just one tick mark, right?
what that? Yeah. Up and down, we're going to count by 1.
Okay.
Or if you think that's too scrunched on yours, if you want to make each thing be a half, that way you can make it go up a little bit higher. If that's going to be too scrunched, feel free to do that.
I like it.
Okay. But we know that at pi over 2 it gets up to 1, or at 90 degrees it gets up to 1, right? At 120 we're back to root 3 over 2. At 135 we're back to root 2 over 2. At 150, we're back to a half. How about at 180, or pi? What are we back to? What's our sine of 180, or our sine of pi? 0. Okay? That's the next one I'm going to put on here. And once you get to pi, we're back to a y value of 0.
Oh, I understand what we're doing now.
Okay?
It was on the TACC, I'm like, I don't know what this means here.
So, the sine of 0 is 0. And then the values kept increasing. The sine of pi over 2, which we also know is 90 degrees, right? The sine of 90 degrees is up here at 1. Then the sine of pi is back to 0. Okay? The next one would be 3 pi over 2, or 270 degrees, right? And I'm kind of counting by 90s. 90, 180, 270. Okay? Ask Lexi.
I just am not liking this. I'm really, okay. You said we're gonna do degrees. Why are we using radians?
We're not using degrees.
Because when you were doing the
But
sine 30, sine 60.
To help you understand, because I don't think you know sine of pi over 6, sine of pi over 4.
Oh, yeah,
You don't know
definitely
those
not.
yet, right?
No,
definitely
But I'm
not.
asking you this. When I say sine of pi over 6, the same question is the sine of 30 degrees, right?
So you're just trying to make it make sense then?
Yes, I'm trying to make it make sense to what you already know.
Okay.
And you know degrees, and you're going to get better at radians, but right now you're not where you want to be quite yet.
Okay.
Okay?
So then. Okay. Well, why are we using the 90, 180, 360 version of radians? And
I don't feel like plotting 0.7 on here or 0.86.
Well, no, I mean, why are you using them in the first place? Because I get, they represent decimals and stuff, but, why do we use those? Just because?
You can use whatever you want. You can count by whatever you want, but look at how these are coming out nice.
Just up.
I want to hit the zeros and the ones. That's all I
Okay.
want to hit.
Well,
If I wanted to, I could put pi over 6 right here, and that would be
so you could do
1/2.
whatever the heck you wanted.
You'll see why you'll want to use what I'm using here, just
Okay.
because it makes things a lot easier to work with.
All right.
Okay? We could put a whole bunch, we could make a table of values with all sorts of x values.
We're just using
I'm
these.
picking ones that I know the answers are going to come out zeros, ones, and negative ones, because if I get that and I kind of see how the pattern's going, I'm going to be able to draw a really nice
Oh,
graph.
that's gonna be a negative one, isn't it?
Okay?
Alright.
So anyway, we kind of made our way up to 1, then we made our way back to 0 here, right? So I'm going to go back to degrees here for a second. Sine of 180 was 0, right? How about sine of 210?
That's the radians.
Negative 1/2. How about the sine of 225?
Negative.
Negative root 2 over 2. How about the sine of 240? Negative root 3 over 2. How about the sine of 270? Negative 1. So when I get to 270 degrees, aka 3 pi over 2, I'm going to be down here at negative 1.
We're gonna go back up to 0.
And then Lainey's figuring this out. When we get to 2 pi again, which would be 360 degrees, right? We'll be back up to 0. Okay? So your sine graph, if I were to graph it from 0 to 2 pi, looks like a wave, right?
Love it. Mine looks weird. Interesting.
So wait, then sine 2 pi, then that's just
Sine of 0.
yeah.
Mhm. So it's back to where I started, basically.
Okay, so
What if I were to keep going?
I assume we go back up to 1 and then 0 and then negative 1.
Didn't we just complete a full unit circle?
Yep. Yeah.
So if we go again, want to just complete it again,
Yep.
and
Oh,
again, and again.
Okay.
So if I wanted to, I could label this next one how much? This is like half pi, 1 pi, 1.5 pi, 2 pi,
2.5.
2.5, which would be what?
2 pi over 2. Nope.
2.5 as an improper fraction, guys? 5 halves, right? 5 pi over 2.
I wasn't even close.
So at 5 pi over 2, you'd be back up to 1. What's the next one? Counting by halves, guys. 1 half, 1, 3 halves,
2 pi.
2, 5 halves, or 6 pi over 2, which is really
3 pi.
3 pi.
Whoa. Now those make sense.
This is like 1 half, 2 halves,
Yeah, I understand.
3 halves, 4 halves, 5 halves, 6 halves.
I
Okay?
understand.
It would keep going, following the same nice wave pattern, right? Yes, lady.
So if you like took that top wave, put it over the bottom wave, wouldn't that make a circle? I
Awesome.
thought that too, Lainey.
Right? Yes.
It's just a circle cut in half and like, you know.
Basically, we took that unit circle and we laid it out lengthwise, basically, to
Okay.
graph it. And so instead of going over and over and over again in a circle, now we're just going out horizontally as many times as we want to. Or let's go backwards. Yeah, I'm sorry, just a second. So,
Oh, you can finish what you were saying.
You don't have to
I saw it.
well, I'm not ready to
I
go
know, dude.
in the backwards direction, but
Okay, so
Gonna
do you
go
remember
down.
when we had like the parent function graph where it's just like straight? Is this kind of like the parent function graph like this?
nice.
Cool
Okay.
beans!
Here is your parent function for all sine graphs that you're going to have to do. You're kind of going to start with this right here, okay? Now, just knowing, this table of values is probably good enough because if you got all that, you figured out the pattern, right?
Right.
You could graph more of it if you wanted to,
Nope.
okay? Let's do it just so you have it,
Oh.
okay? So this would be negative pi over 2, right? When x is negative pi over 2, what's my y value going to be?
Negative.
So negative pi over
Negative
2, I'd be down here at negative 1. How about at negative pi? So negative pi means I'd go this way, so I'm really at over here, right? What's the sine value over here? 0. How about negative 3 pi over 2, which is actually straight up here? What's the sine value? 1. And then all the way back here to negative 2 pi, you're back to 0 again.
I want it now.
There is your parent function for all sine curves. And I don't know how far you graphed it on your sheet of paper, but up here on the board I have it graphed all the way from negative 2 pi to positive 3 pi. Not for any particular reason. I could keep going if I have more board space in this direction or this direction. I could keep going. You guys got the pattern down. Okay? Or in degrees, I essentially graphed it from negative 360 degrees all the way to 540 degrees, right? Everybody okay with that? Okay, so that is my sine curve. It repeats, it's a pattern, because it's like going around that unit circle over and over and over again. Okay? All sine and cosine graphs will be waves. Sine and cosine graphs will be waves, just like this.
What's tangent?
Okay? Tangent's a little weird. It repeats still, but it's got some asymptote, because remember how tangent is undefined sometimes?
Yeah.
So there'll be some asymptotes on that graph. We're a little ways from graphing tangents. We're going to really focus on sines and cosines for now. Okay? So this is my sine curve. You're going to hear me use the word amplitude. Maybe not much more today, but amplitude is really like your wave height. The height of the wave. Okay, yep. So if you envision this as a wave, okay, I want to know the height of this wave. Well, let's pretend all of a sudden there wasn't a wave. Let's say this is water, okay, and all of a sudden there wasn't a wave. Where would level water be located on this graph? Right here along the axis, right?
Yeah.
So if there was no wave, the water would be level right there on the x-axis. So because this is level, what is the height of this wave?
I don't know if it's 1 or 2.
1.
Okay.
Okay? 1. Because if this is level, how far above level does the wave get?
1.
If this is ground level, okay, or what you do is water level, how far above water level does the wave get? 1 in this case, okay? So the amplitude for your sine curve, for this graph, the amplitude is 1. Because it only goes 1 unit above what we call, level water.
Do we consider the fact that it dips down one,
Yeah,
like below
and what-
0?
Yeah, but that would just be total displacement from top to bottom.
Will you ever ask that?
No,
Wait, so
that's more of a physical science type stuff.
I'm pretty sure we did that. Or
Mhm.
that's
You're
why I
saying
was
if it's
confused.
above
Well, I
one,
remember
the
totally
amplitude is 1.
displacement.
Like if it's above the x.
Basically, take how far it is from top to bottom and cut that in half.
Oh, okay.
Okay, so because there's 2 units from the top to the bottom, the actual height of the wave though is half of that. Okay? Because the water level is not really down here. You know how waves work, obviously, when you have a wave that's lower than that behind there and in front. Okay?
Wait, but is it always going to be even the amount that it goes up as it goes down?
Yes.
Okay, just make sure.
For the ones we do.
Okay.
Okay? Alright, so there is your sine curve. Alright? You will want to do the cosine probably on the graph right below, but I'm going to do it in the same one so you can kind of see the relationship a little bit.
Okay.
Okay?
So this would be graph cosine x.
So now I'm going to graph, I'm going to do y equals cosine x. Okay? I'm going to go back. Miss Carey always said to use -2, -1, 0, 1, and 2, right? In those table values. For trig, we're going to use these. We're going to use 0, pi over 2, pi, 3 pi over 2, and 2 pi. Basically 0, 90, 180, 270, 360. Okay? So, I'm going to take 0, plug it in. Trinity. What is the cosine of 0 radians, or the cosine of 0 degrees?
1.
1. Very good. So the cosine graph's actually going to start up at 0, 1. Okay? Pi over 2. Julia. Pi over 2 is like 90, right? It's like half pi. Because 1 pi is here, so half pi is straight up here at 90. So really you're just thinking, what's the cosine of 90 degrees? 0. Okay? Pi, Lexi. So that'd be right over here.
Okay.
What's the cosine over here at 180 degrees, or at pi?
-1?
-1. Okay? 3 pi over 2. So that'd be right down here at 270 in a sense. What's the cosine value at 270?
0.
0. And then 2 pi is back to 1 again, right? Very, very similar.
Just one.
Just kind of shifted a little bit, right?
Yeah.
Yeah. Which, if you think about it, guys, when you do your time test, aren't your sine and cosine answers almost the same all the time. They're all 1/2, root 3 over 2, root 2 over 2. Just depends what quadrant they're in. So if you shift the cosine, you can make it match the sine. But the reason it is different is because in certain quadrants, some of them are negative, some of them are positive. Okay? I can keep drawing this, right, if I want to. If you want to go all the way to the same values. Okay? So there is your cosine curve. Okay? Another thing I'd like to point out. Between 0 and pi over 2, isn't this the first quadrant? Between 0 and pi over 2? Between 0 and 90 degrees, is that the first quadrant?
Yeah.
Nope. Yes.
0 and 90.
Yes.
From 0 to 90, isn't that all first quadrant?
Yes.
Look where both graphs are. They're both above 0 because sine and cosine are both positive in the first quadrant, right? Let's look at the second quadrant. What's positive? The blue one, which is your sine curve, right? Sine is positive in the second quadrant. Cosine is negative in the second quadrant. Let's go to the third quadrant.
Both negative.
Both negative. Fourth quadrant.
Cosine is positive.
Cosine's positive. Yeah, see that connection there?
I think the one thing that's throwing me off is that the fact that our our quadrantal angles are on just the x-axis, and so it's just confusing me. But I think I'll get it eventually.
We could count by 1 if we wanted to, like you always have. You know, when you make your x and y axis, you count by 1s up and down, you count by 1s left and right. You certainly could. The problem is then, do you know what the cosine of 1 radian is? No. Because essentially then I'm asking you, what's the cosine of 57.3 degrees? Remember how we said 1 radian was about 57?
Yeah.
We don't know that one. So I'm picking values where I know the answers to really quick and easy, and they're nice answers like this.
Okay.
But if you wanted to count by 1s, essentially then, you know, you'd be looking at, you know, 1 would be about right here, this would be 2, this would be 3, because pi is a little bit more than 3. Yeah, I mean, so you could, but then you got to kind of estimate where pi over 2 would fall and where pi would fall. You know, so we just, to avoid that, I mean, nobody ever says we have to count by on a certain scale on our graph, so let's just make our scale be numbers that are nice for us to plot. Does that make sense?
Yeah.
Okay. So there's your sine and cosine graphs. We'll do some practice with them here, but I'm going to shut the video off for right now. Any questions that might be helpful for the video before I shut that down?